All right, so this video is going to be on three-dimensional graphing. A three-dimensional graphing system is, or at least how I draw my coordinate systems, is I draw X coming out of the paper and Y, Z flat on the piece of paper. So again, Y, Z is flat, X is kind of coming up and out at us, out of the computer. I'm gonna start with graphing a fairly complicated example because I want to introduce a couple other things with it. All right, so this example, this shape is called a hyperbolic paraboloid. Hyperbolic paraboloid. The equation of this shape is z equals x squared plus y squared. So notice it's got an x, it's got a y, it's got a z. This is putting us into that three-dimensional space instead of just an x and a y. And I've already drawn the wrong thing. Let's try again. So z is equal to y squared minus x squared. Okay, so what this looks like, so pay attention to drawing this one. Again, I'm drawing the most complicated one right now. I just want to state that again. On the zy plane, we've got a parabola. Then on the tips of each of these parabolas, I draw another parabola. One going from long to short, and another one going from short to long. And then I connect long to short and long to short. Okay, so now this has quite a few parabolas going on in it. First of all, it's got the obvious one on that YZ plane. Then it's got a not so obvious one here on the XZ plane that goes like that. So that means that that point 0, 0, 0 is a minimum and a maximum. Kind of keep that in mind. That's going to come up later. It's a maximum in the XZ plane and it's a minimum in the YZ plane. Then we have another one, or another few parabolas. If we were to squish this flat on the XY plane, we would see parabolas there and there, and well, all along there. But there's some other parabolas there. Now, I want to talk about something called traces. So each different one of these colored parabolas that I've drawn on this shape, each one of those can be called a trace. Now, if you're at all confused about how to draw these things, traces can be a great way to go. Bring it back to 2 dimensions and then expand it into 3. So for instance, we could draw traces on just the YZ plane. So when we do this, we're going to be drawing just the YZ plane. Now, in order to do this, because it's the YZ plane, we'd need to pick different values for x. So, I don't know, let's say that x is equal to 0. So, when x is equal to 0, that gives us the equation z equals y squared. So, that would be a parabola, z equals y squared. There's that parabola right there. Now, we can do multiple ones of these. So we can also say, let's try when x is equal to 1. Now, when x is equal to 1, this gives us the equation z equals y squared minus 1. So now that is a parabola that is one below this one. It's one below that one. So this is the trace. I've just drawn the trace now when x is equal to 1. Before I drew the trace when x is equal to 0. Now if I bring this back to our three-dimensional drawing, when x is equal to 1, so this comes out of the x-axis, we're going to see another parabola right here. That is one below the other blue one we just drew. So it's kind of out of the board on that shape. So out of the computer, and because it's out of the computer, this shape is dropped lower than it was below. All right, so each different one of these is called a trace. So let's do another trace. Let's do some traces on the XY plane. So on the XY plane, traces on the XY plane. This is also referred to as a contour map. And the reason being is if you think of any kind of like a topographical map, it's a two-dimensional space, but it gets across three-dimensional properties because it puts the contour lines for each different elevation. So if we looked at a contour map of Humphreys, it would have a bunch of kind of lines that would go around in a circle each one would represent a higher elevation as we were trying to kind of go up the mountain. So that's why the XY plane is referred to as a contour map. So if you hear contour map, it means just find the traces in the XY plane. So that means find the traces at different elevations. So different heights, different z values. So when z is equal to 0, we go back to this equation, set z equal to 0. So that gives us that 0 is equal to y squared minus x squared, which is when y is equal to, I had to take the square root, so I get a plus or a minus x. So on the xy plane, let's see, how did I do this before? In green. So plus or minus x, well, there's y equals plus x, there's y equals minus x. Those lines are, man, they're going to be kind of hard to draw on this. Right there, and back behind it, and in front right there. So there's those lines. Then let's do another one of these. Let's set z equal to 1. So this is going to be the trace when z is equal to 1. And that is when 1 is equal to y squared minus x squared. These are a little bit, this is something you probably haven't drawn very much of. This is two different parabolas, both at 1, right there, and right there. So this was when z was equal to 1. I'm going to specify when z was equal to 0. And I already have those z equals 1 drawn on this graph. Right there and right there. Those are the contours when z is equal to 1. So at an elevation of 1, if we were to stay at an elevation of 1 and walk at that elevation of 1, we would walk around this parabola. It's another way to think about that. Okay, so lots of stuff with this drawing. The traces, the contour map, and the point I want to get across here is on any of these drawings, if you forget how to draw them, draw a trace, set x equal to 0, or y equal to 0, or z equal to 0, and see what you get. And if that doesn't work out for you, set it equal to another number and kind of see what the shapes look like on a two-dimensional plane and bring that back to 3 dimensions. Okay, so now, lots of other shapes here. I'm going to go a lot more quickly through these other ones. These are all shapes that I expect you to know how to graph. I expect you to know how to graph all of these by hand. So sphere. So let's say that x squared plus y squared plus z squared is equal to 4. So this is a sphere, x squared, y squared, and z squared, all positive. The radius is 2, so I'm going to draw a circle in the YZ plane. I'm going to draw an ellipse more just to give it that kind of shape in the XZ plane, and I'm going to draw another ellipse in the XY plane. Notice that I'm not a great artist, but you could just get across the idea of the shape. You want the idea of the shape, and you want how big it is. So let's mark how big this is. 2, 2, and 2, all on each axis. So it's too big everywhere. We could center the sphere elsewhere. So let's just say that I've got x squared plus y, let's go minus 1 squared plus z squared equals 4. So shifting properties of graphs work exactly how they've always worked. So this is going to shift over 1. So from that y equals 1 position, all the other ones are still 0. We now have a radius of 2. Another circle there and another circle there. All right, so there is our, so that would be -1 and 3. So that gives us, that's what happens if the sphere is not centered at 0. This one, the center right there is at 0, 1, 0. All right, so there's the sphere. And ellipsoid. An ellipsoid is a sphere that's stretched. It's sort of more like a football, maybe. So here's an example. Let's do x squared plus 4y squared plus 3z squared equals 12. This would be a good one to use traces on. How I do this one is just with intercepts. I find out where this is going to cross the x-axis, where this is going to cross the y-axis, where it's going to cross the z-axis, and then I know because the x squared plus y squared plus z squared that it's going to be circles or ellipses. So where it crosses the x-axis, I'm going to ignore y and z, and I get that x is equal to, let's see, if I ignore y and z, I've got x squared equal 12, so x is going to be root 12, so that's somewhere in between 3 and 4. 1, 2, 3, 4. So somewhere in between 3 and 4, right there. Root 12. 1, 2, 3, 4. Somewhere in between 3 and 4. That's root 12. Okay, so that's where it crosses the x-axis. The y-axis, I'm going to ignore x. I'm going to ignore z. I get 4y squared equals 12. So that means y squared equals 3. So y is going to be plus or minus root 3. So 1, 2. So that's less than 2. Root 3. So that was negative root 12 back there. And there, negative root 3. And one more here. And we've got to ignore x and y. 3z squared equals 12. That means z squared equals 4. So z plus or minus 2. So there's 2. There's negative 2. Now I have to cross these dots, and when I do this, I concentrate on each plane. So y and z, I've got root 3 and 2. Negative root 3, negative root 2. Then how about, let's concentrate on x and z. So that would be z is 2, x is root 12, negative 2, negative root 12, and 2. And let's see, one more. Which one haven't we done here? We have not done the yx. negative root 3, root 12, negative root 3, root 12, negative root 3. And now you can get the idea of that kind of football-looking shape. Once again, notice that's not a fantastic drawing, but at least gives me the idea that this ellipsoid is stretched more in the x direction. All right, let's see, elliptic paraboloid is next. Elliptic paraboloid. So an elliptic paraboloid, general equation of this would be z equals x squared plus y squared. And an elliptic paraboloid looks, I always kind of consider this to look like a bowl. There's our paraboloid, and there is either a circle, in this case it is a circle. Once again, we could go to those traces. When z is equal to 1, you get 1 equals x squared plus y squared. That is a circle and not an ellipse. But just like an ellipsoid, we could stretch this. Just like anything else, we could center it not at the bottom being at 0, 0, 0. Okay, a couple others here. That was the elliptic paraboloid. A cone. Cone looks like z squared equals x squared plus y squared. Another way to write this would be to take the square root, in which case we get a plus and a minus. A cone has a positive z part and a negative z part. X, Y, Z. So the full cone actually looks like it looks like an hourglass. And then we've got a cylinder. So a cylinder looks like, an example of a cylinder would be 4 equals x squared plus y squared. And I'm hoping that kind of what you're thinking now is, well, isn't that a circle? And the answer is yes, that's a circle. And so it depends on the context of the problem, whether 4 equals x squared plus y squared, whether you're talking about a circle on the xy plane or whether you're talking about a cylinder where z can be anything in a three-dimensional plane. So that just depends on the problem. All right, so there's my x, y, z. There's my circle of radius 2 on that xy plane. But if I'm going to draw this in 3 dimensions, z can be anything. Now here's how I draw when z can be anything. I draw lines parallel to the z-axis. If x were anything, I would draw lines parallel to the x-axis. And I'm going to put another circle up here just to end that cylinder, make it actually look like a cylinder. All right, so moral of the story here is that even 2-dimensional graphs can be brought into a 3-dimensional space. And one more, this should be sort of review, drawing a plane. Planes look like a number times x plus a number times y plus a number times z equals, c times z equals d. So A, B, C, and D are numbers. An example, let's do x. Let's see, just trying to think about what this would look like. Let's do this all positive, makes it a little bit easier to see. X plus 2, y plus 3, z equals 6. Planes I again do with intercepts. So I want to find out where this is going to cross the x-axis. And in order to do that, I'm going to set y and z equal to 0. And I would get x equals 6. 1, 2, 3, 4, 5, 6. X equals 6. Then I'd want to find out what y is. So I ignore x and z, set them equal to 0. I get 2y equals 6, so y is going to be 3. 1, 2, 3. And for z, I'm going to set x and y equal to 0. So I get 3, z equals 6. So z is going to be 2. Connect the dots. Connect the dots. And so the plane is this piece of paper here. It is infinite, but you know, we have to end things to make it apparent what it's doing. So it's infinite and it's going back into the piece of paper. Okay. So just as a little bit of a recap, I do expect you to be able to recognize that, say, for example, z squared equals x squared plus y squared. I expect you to recognize that that's a cone and be able to draw it. Traces can be a good way, if you forget what something looks like, to figure it out. You can draw a couple traces on there and say, oh yeah, that must be a cone then. So figure out what it looks like in the XY plane. And the contour map are the traces specifically on the XY plane.